understanding routers. In the previous videos in this series, we've been looking at switches, we've been looking at how to build local area networks and how to configure features on switches so that we can build LANs. We're now going to start to move away from that and look at how we can build wide area networks, and more specifically, how we can configure features and functions on a router. So we're going to be moving away and looking at the big picture of how we can build networks, large networks, so that we can connect multiple networks together, so that we can have devices across the world being able to communicate with each other. So before we go into depths about what routers are and how they work, let's just go over some information that we covered in a previous video. So routers themselves reside at layer 3 of the OSI model, which is the network layer, and their main job is to connect our networks together. So with routers we can build WANs, and the routers will route packets between those WANs. The router will route packets between our LANs so that we can build a WAN. And so the main job of the router is to just get us off our network onto another network, whether that be the internet or another enterprise site. And like a switch, a router has what's called a routing table to make forwarding choices on where to forward the packet next. So with the switch, we looked at the CAM table or the MAC address table, as it's more commonly known as. And we looked at how the switch can use this table to make a choice on where to forward the traffic next. We looked at how we can use this table so that it can make a choice on which port to forward this packet out of. Same thing with a router. A router will look in its routing table when it receives a packet. It will look in its routing table to make a choice on where to forward that packet next. So whether to forward the packet out an interface, who's the next router in line to reach that device, or whether it's actually connected to the network that the destination device resides in. Routers are software based, so it means that they're slower than switches because everything is done in software. However, they have more features than switches because it's easier to add features to software rather than having to build hardware chips to perform those features and functions. So, like I mentioned before in the previous slide, routers use what's called a routing table to forward traffic, and this screenshot shows a basic routing table and what the routing table looks like. So the code just define the different routing information sources a router has learnt of routes from. So a router can learn of routes from different sources. So we can either tell the router how to reach a destination network, or it can learn it from other devices using a routing protocol. The routing table will list how the router learned that route, the network that is reachable, who the next hop is, and the outgoing interface. So this says that I can reach the 10.0.0.024 subnet by using this next hop and by forwarding the traffic out this interface. I can also reach this network by using this same next hop and by forwarding the traffic out this interface. And I'm connected to this network. So as we can see, the routing table is different to the MAC address table. We're kind of dealing with networks and what next hop we can use to reach those networks, and the interface that we can use to reach that next hop. We can also see how long this route has been known for, and I guess, like I said before, how the route was learned. So the two numbers in here, which won't mean anything now, but will mean something when we get onto how to configure routing protocols, are the administrative distance and the metric. The administrative distance just describes how believable the route is. So the way it works, we'll go into this in more depth in a later video. But when a router learns of different sources, so imagine that this router learned of a route to this subnet via EIGRP, via OSPF, and via BGP. Just as an example, these are routing protocols. Which route does it see as best? So is learned of how to reach that network from 3 different routing information sources. And imagine that we also create a static route telling the router how to reach that network. Which one does it believe? Well, It believes the route was the lowest administrative distance, and different routing information sources have default administrative distance values. And so the way it works, the lower the administrative distance is, the more believable that route is, and the more preferred that route is. But we will go into administrative distance in another video. So when we look at a switch, we can see all the external connections. So we have the power cable here. Unlike a switch, this is a router, not a switch, but unlike a switch, a router has got a on-off switch. So instead of having to yank up the cable in order to power the switch off, with a router we can just turn off the power button. Routers themselves come with what we call WIC modules. So the way it works, that with the WIC modules we can add the interfaces that we want to a router, which makes a router more customizable than a switch. So normally with switches, they come as the built-in interfaces, normally fast Ethernet or gigabit Ethernet interfaces. With a router, it comes with one or two built-in interfaces, but we can add more ports, more connections to it, more interfaces to it of different types by adding different WIC modules. So we can add we can add more Ethernet ports, we can add what's called serial ports, all types of different ports to it by changing these WIC modules. And we can see the RJ45 port here, the aux port. This here shows a mini USB console port, and we also have what we call compact flash. So these are slots which allow us to add additional flash memory to our router. We can do the same thing with certain Cisco switches, and in which we can add more. We can increase the flash memory, so we have more memory available on the device itself. This shows the built-in interface as being a gigabit interface. As you can see, it's got two built-in interfaces. If you wanted to add more, then we can add more WIC modules to the device. And they literally just unscrew and screw the new WIC modules back in. It's got two USB ports. So some newer Cisco devices come with USB ports, so we can transfer files, do any backups or any file transfers via the USB port rather than having to use a TFTP server or something like that. So each port on a router represents its own broadcast domain. So one of the main jobs of routers is to segment our network so the traffic needlessly doesn't leak over from one network into another network. So if each port represents its own broadcast domain, which means that unlike a switch, if a router receives a packet or a broadcast packet or broadcast frame on one interface, it's not going to forward that broadcast packet out any other interface, which limits our broadcast domain. Also, each interface on the router we would have to configure an IP address. Because each port represents its own broadcast domain, each port is essentially in its own network, so we would have to configure an IP address on each individual interface on the router. So just to visualize this, imagine this is a router, this is one interface on the router, this is another interface. These would be in separate broadcast domains. That means if the router receives a broadcast packet on this interface, it's not going to forward it out of this interface at all. Because each port represents its own broadcast domain, the IP addresses we configure go on the port. With a switch it was different. With a switch, the whole switch represented the broadcast domain. So each port would be in the same broadcast domain unless we use VLANs, and to configure an IP address on the switch, we would have to configure a SVI, a switch virtual interface. Then the IP address would go on the SVI. With the router is different. The IP address goes on the actual interface at the interface level. And the router, what it'll do is that the main job of a router is that it's gonna, when it receives packets, normally the packets will not be destined to the router itself. Normally those packets will be trying to use the router to get to another network which is far away. What the router will do is going to look at the packet, choose the best route from its routing table to reach that destination, and then it's going to send the packet along the route so it can get to the correct destination device. So how does the router forward a packet? So let's look at the forwarding process or the routing process on a router. So the router is going to receive a frame and it's going to look at the data link information. So this is assuming that we are receiving a frame on an Ethernet based network. Let's just assume we are to make it simpler to understand this routing process. The data link information is going to say, let's say PCA send this frame and this frame destined for me, the router. So the router is going to see the frame destined for him, and then it's going to start to process that packet. So it's going to remove the data link headers and look at the layer 3 headers to see if this packet is destined for him or if this packet is trying to use him to reach another device. And so it's going to look at the packet, and if the packet is destined for him, so if the destination IP address is one of the IP addresses on the router, then fine, the router will process the packet and look at the data. If not, if the layer 3 IP address, the destination IP address, is a different IP address, so an IP address not configured on any of the router's interfaces, it's going to understand that the source device doesn't want to communicate with the router itself. The source device just wants to use the router to reach another destination device. So then it's going to now try to route the packet. What the router is going to do is going to look for an entry in the routing table that matches the destination IP address. So we looked at the routing table in a earlier slide. It's going to look through that table to find the best route or the most specific route that matches that destination IP address. So in this case, let's say the destination IP address is 10.1.1.1, and it finds a route which is the most specific route that says that to reach 10.1.1.0/24, then use this next hop. It's going to consider that as a match for the packet, because that is the most specific route that matches the packet, and the range of IP addresses covered in that route, covered in that destination network, includes the destination IP address. So then it's going to consider to have found a match, and it's going to forward that packet out of the correct interface to the correct next hop. But before it does that, it's going to then re-encapsulate the packet in a layer 2 header and trailer and forward it out the correct interface to the correct destination device, to the correct next hop device. Now, depending on what interface it's forwarded out, will depend on what kind of layer 2 information we're going to put on it. If it's being forwarded out an Ethernet interface again, there's going to be a source and destination MAC address. If it's like a serial link, like a PPP interface or HLC interface, it's going to have no layer 2 information on it. And when we get to WAN protocols, we will discuss why that is. Or if it's like a frame relay interface, you're going to have frame relay information on it. So there's a type of layer 2 information, and the type of layer 2 header will depend on the type of interface we're going to forward that packet out of. So now let's see the IP routing process in action. So in this case, PC1 over here on the left wants to communicate with 2.2.2.2. So this 2.2.2.2 is a web server which resides somewhere on the internet. Okay. Now PC1, we've talked about how a device knows where to forward a frame we talked about how a PC knows whether or not the destination device resides in the same network as itself, and whether it should forward that frame to the router or forward the frame directly to that destination device. So in this case, it's already done that comparison, and PC1 knows that 2.2.2.2 doesn't live in the same local area network as himself. So PC1 is going to have to send that packet to the router in order to reach there. So in the source MAC address, it puts its own MAC address. That the destination MAC address is going to put its the MAC address of R1, which in this case is 0800.1111.22.2. The packet is sent over the local area network through the switch to R1. The next in the process is that R1 is going to receive that frame. It's going to look at the destination MAC address and see that this frame is addressed to him. So this frame isn't like a broadcast frame, or a multicast frame addressed to a specific group of people. You see that this frame is destined for him, so it's going to then remove the layer 2 headers, the source and destination, so the layer 2 headers, the Ethernet header and trailer, and it's going to look at the upper layer, so the layer 3 header, to find more information about this frame, about this packet. So to find out if the packet is destined for him, whether this packet is destined for somebody else, and this guy's just trying to use him to reach that guy. So the router, so R1, sees that this packet isn't actually destined for him. This packet is destined for a device with IP address 2.2.2.2. So the next thing R1 has to do, it has to find out how it can reach 2.2.2.2. Okay? If the router doesn't have a route, it will just simply discard the packet, because it's going to be like, I don't know how to reach that guy, so there's no point of me even trying to forward this packet on to anybody else. I'm just going to discard and drop the packet. So what R1 does, it looks in this routing table, and this route over here is the closest match. So normally, you'll see with routers, they wouldn't have an exact match for that destination IP address. They would have a match, a very specific match, or a match in the routing table that shows how to reach a range of addresses, normally a network. So in this case, R1 has got a route to the 2.2.2.0/24 network, which is the network that 2.2.2.2 resides in. And because this is the most specific route in its routing table, R1 doesn't have a more specific route in its routing table. It's going to use this route to forward the packet on to the next hop, so this packet eventually gets to 2.2.2.2. So this route says that to reach 2.2.2.2, forward the packet out interface far east of 0.2, this interface over here to the ISP, and forward it to the next hop of 10.1.1.1. So now that R1 has all their routing information, it knows where to send the packet, and it knows which interface to send the packet out of. Now, because that interface is an Ethernet interface, it means that it uses Ethernet-based rules in order for two devices on that same network to be able to communicate. So the next thing R1 has to do is it has to find out the destination MAC address of 10.1.1.1. In this case, the destination MAC address of 10.1.1.1 is 020023114333. So R1 is going to build a layer 2 header, put its MAC address of FA0/2 as the source MAC address, and it's going to put the MAC address of 10.1.1.1 as the destination MAC address, and now forward the frame out fast eastern 0/2 onto the next hop, which is going to be, in this case, let's say, imagine it is router R2, so 10.1.1.1. And 10.1.1.1 is going to do the exact same thing as R1 when it goes to forward the packet. It's going to receive the packet, sees that it is destined for him, because it's going to process the packet further, sees that it's not really destined for him. The original sender of this packet is trying to reach 2.2.2.2, and it's trying to use 10.1.1.1 in order to reach that device. It's then going to look in its routing table and try to find the most specific route which matches this destination IP address. So, by most specific, I mean the route that so it's just the most specific route. So when we get into subnetting and stuff, you'll see that we don't have to follow the class A, B, or C rules for the subnet mask. We could have a class A, B, or C address with what we call variable length subnet masks, and so the route is going to have a lot of different routes in its routing table with different subnet masks. When it chooses which route is best, it's going to choose the most specific route. So the route with the longest subnet mask, which in binary matches the most number of bits on that for that destination IP address. But we will see that once we get into subnetting. So we have reached the end of this video, and we have seen the basics of routers. We've seen how. So we've kind of had a recap on what routers are, what they're used for, that the layer 3 devices used to route between networks, used to build WANs, wide area networks, and the whole idea is that before we start to configure our routers, we're just going to slowly ease ourselves away from looking from a local perspective of our network, and kind of branch out and have a bigger picture of how we can build wide area networks, so we can connect these local area networks together. We've also seen, which is probably the most important part of this video, we've seen the routing process on a router. So we've seen how a router actually forwards a packet from source to destination. So how it receives a packet, strips away the headers, looks at the destination IP address, and forwards the packet based on the destination IP address. When we start to configure routers, we will see this process in action, but it's just very, very important to understand the forwarding logic behind how a router knows where to send a packet next in order for that packet to carry along its journey to reach that destination device in the end. I hope this has been informative for you, and I'd like to thank you for viewing.